Thank you for joining this workshop. Today I will talk about our work about high force software robots with autonomous control. And basically we will focus on how we can unleash the tether of many software robots and can make the system really practical. And the ultimate goal is for translational medicine. In my lab, we focus on two areas. On the left, we call this the domain of robotics. Basically, we design actuators and sensors, and also we design robots from scratch, and we embody control and intelligence through controller development. For example, we develop some really very special enabling technologies, including high-speed software actuators, and we also are using software robots to help manipulation of infectious materials to tackle this kind of a pandemic. On the right, the second domain is we call this scientific discovery. We believe that the robots could be for medicine and also even as medicine. We primarily focus on robots for minimally invasive surgery using some software steerable catheters, and also robots for to enable community-based rehabilitation, to enable a paradigm shift from a land-based solution to community-based solution through some a portable, lightweight actuator and lightweight robots. In terms of our robot platform, we have designed several robot platforms in the continuum care, ranging from disease prevention using our industrial exosuit. This for to prevent musculoskeletal injuries. We also developed MRI-compatible robots for prostate biopsy for cancer diagnosis, and also neurosurgical procedures for cancer treatment. In the last 4 years, we have been focusing on software robots for pediatric rehabilitation and also for people with musculoskeletal injuries. We believe that wearable robot can not only help people with neurological disorders like with stroke, spinal cord injury, but it can also help people with musculoskeletal injuries, those kind of population. In my lab, we have a multidisciplinary team covering mechanical engineering, electrical engineering, control, and biomechanics. We also collaborate with experts in biomedical engineering. When we started the wearable robot project, the first question we asked ourselves is, what are the fundamental limitations of wearable robots? If we observe wearable robots through the lens of design and control, if we think about the design, many wearable robots, in particular those industrial ones, have no difference with those kind of industrial robots. And certainly there's some great work about tethered exoskeleton to understand the benefits of wearable devices. Our goal is to really unleash the tether, make the robot really lightweight, and not really rely on tethered actuation or tethered power sources. So the robot can really reduce energetics and also optimize many other aspects of human performance. If we think about it through the perspective of control, we certainly want the robot to be really, really versatile, that it can do many different activities. Today I will talk about, first I will go over some our work about compliant wearable robot design. Then I will talk about software material wearable robots. Then I will talk about robots with some kind of autonomy. In terms of high performance exosuits, we have been thinking about the fundamental limitations of wearable robots. For example, we think motor is certainly one of the key limitations. We also agree with Dr. Bobby Gregg, and the motor certainly is one big barrier, both in terms of its performance and also its cost. And the second limitation is many robots are still rigid, and we want to develop some software transmission mechanism, like using cable elastomer. But in addition to this, we also want to develop some a high performance pump, because the pump is really crucial for software robot actuation. If we think about the revolution in automotive industry, we believe that this quasi-direct drive actuation is also kind of like similar to this what do you see in terms of automotive industry, because if we can design high torque motors and we minimize the gear ratio transmission, we can certainly optimize the compliance, actuation bandwidth, and even overall efficiency of the system. And this had been kind of like a little bit older problem, like Professor Asada already started this more than 30 years ago. But I think with new solutions in electronics and magnet technology, we have some new solutions that can realize this important goal for the robotics community. In general, our robot has a better torque density than the Maxon motor. If you look at the torque density and also the power density. And overall, we want to optimize the torque and reduce the speed, because the high speed could be dangerous for human-robot interaction. In addition to some motors, like the T motor we mentioned in the earlier of this workshop, because it's basically developed for the drones, it really have a high speed. And for wearable robot, we still want to lower speed and higher torque. So in my lab, we have been focusing on the motor design optimization, including motor topology optimization to optimize the exterior rotor instead of this interior rotor. And we also optimize the motor like a housing and also the material to have like a optimization in terms of electromagnetics, mechanical, and electrical performance. So our robot is really, we believe, is that the most lightweight powered exoskeleton, because it's not only because of the high torque motor. There's certainly one part of this equation, and also the second factor is a simple design. When I talk about what I mean simple is because mechanically you can see it's very have very simple structure, and also in terms of electronics we have very compact electronics that is basically like a smartphone size that can be worn by the person. So overall, we believe that the robot can provide a higher torque assistance than state-of-the-art solution. And we also think the robot can reduce more energetics through this simple motor design and a simple robot design. The second topic I want to cover is high performance software robots. I will start from like a software actuator, and similar to the rigid actuator, we also envision a revolution in software actuators like automotive industry. As you can see, most software robots are still tethered. They use quite a heavy and bulky pump and provide some like a not very efficient pneumatic actuation to the user. And in our design, we have been developing hydraulic and electro-pneumatic actuator. So the overall, the actuator itself could be less than half kilogram, and the system has a much better efficiency, but it can produce human level forces up to 500 Newton. In addition to the motor technology that can be used for rigid robot and actually also used for the software robot, we also need some like a pump technology. And the standard motor has a mediocre efficiency, and also the pump, this kind of like a large pump, the efficiency is also very low. In my lab, we have been developing some like a magnetic pump that can produce some like a non-contact based transmission. And our motor is basically very similar to the high torque density motor we used for the rigid and the compliant robot. And for the efficiency is higher than conventional solution. That's because it operates at like a high torque and a low speed like a torque speed profile landscape, and also our pump has higher efficiency than this kind of like a heavy and bulky pump. So overall, we can significantly increase the pump based on our modeling. Certainly, we need to do more experiments to validate this kind of like performance improvement. In addition to the motor and the pump solution, we also work on the transmission innovation. For example, we work on like a pneumatic actuator. We call this a bistable actuator, published last year in Science Advances. So basically, this kind of actuator can produce much higher speed than traditional, about 20 times faster than traditional soft actuator. In addition to overground locomotion, it can also be used to design some underwater robots. And I think what's really cool is using the same principle, we can also design using this bistable actuator, we can also design high force manipulator, like a gripper, and it can lift up to 11 kilograms object using this kind of like a simple robot design. I think what's unique about this kind of like a design solution is through the spring modulation, we can also modulate the stiffness of this robot. So it's a high force and also variable stiffness software actuator that can be used for many robotic applications. In addition to pneumatic solution, we also explored hydraulic actuation. And our hydraulic actuator can generate up to 500 Newton force, basically human scale force. But the actuator itself, you see this kind of like basically motor pump structure overall is less than 300 grams, roughly 300 grams, less than 400 grams. And it can generate kind of like a high force for modular actuation for the hip and the knee. So in general, we believe that we can get away from this tethered low efficiency actuation to this untethered magnetic pump and electromotor based actuation. The third topic I want to cover is how we can embody autonomy to the robotic system. Through our modeling and experimental evaluation, we found that our actuator with the cable actuation or with the gear actuation has a really low residual torque and also can maintain high bandwidth. So those are really crucial for high performance robots. And in addition, we have been working on some learning-based controller, like reinforcement learning-based control. I think the general goal is we want to get away from this standard phase dependent control. The standard solution is still using a state machine or using some like a phase variable. We want to kind of like get rid of this. We haven't fully understand this problem or the solution yet, but we believe that if we can use this kind of like a phase independent assistive control, we not only we don't need to calculate the phase gate phase, but also the robot can autonomously determine the optimal control profile. I think that will be really useful. The robot will be really intelligent and autonomous using this kind of like data-driven autonomous data-driven reinforcement learning. So my postdoc Susan has developed some like optimization method and also implemented some controller in the simulation environment in collaboration with Dr. Zhou and NGIT. We think this method works very well in simulation. We are working on the like implementation of our hardware. Through our initial testing, we found that the robot can assist forward walking, backward walking, stop motion, and actually also, like Pauline mentioned, we can actually assist up like a stair climbing and a stair descent, this kind of like activities. So we believe that this method could be very ubiquitous for several different kind of activity assistance. With that, I will like to acknowledge our collaborators and the funding agencies to enable us to study soft robots to empower human and other translational medicine. Thank you.